center it at -1, and then I also take this and center it at +1. So that's kind of like if I have -1 here. This thing has a width of 4. Okay, or yeah, sorry, it has a width of 4. So this means I have to go out to -3, and go all the way to 1, +1. That's not evenly spaced at all. Okay, so that's sort of like the first one. Now I need to take this and I need to center it at +1. So that means it's going to go between -1 and +3. Okay, so I need to use superposition though. So wherever there's overlap, I need to add those two pieces together. So really, I've got 1 + 1, so this should be up at 2. So that's what you should have got. Okay. I saw a lot of sync functions on there. All right. When would you have a sync function?
Frequency domain.
Right. So if I was actually not convolving these two signals, but if I was multiplying, like if this was,
if you put in a sync function.
What?
If you put in a sync function in a time domain for some reason, that's when you get.
Right. If you're multiplying two signals, if you're multiplying a cosine.
Yeah, that's what I was.
Okay. If you're multiplying a cosine by square pulse, then you're convolving their Fourier transforms, which would mean that you're convolving this function with the sync function, which is why you get two sync pulses at -1 and +1. But we're just directly convolving these signals, so didn't get this guy. All right. Any questions?
But isn't it like technically, aren't you convolving like two square pulses together?
No, convolving square is two.
Yeah, but then since they overlap, are you convolving the two squares together, or are you just adding them at that point?
You're just adding them wherever there's over. It's superposition. Okay, because you're imagine convolving this with only the first impulse, and then imagine convolving it with only the second impulse.
And then you add the.
And then you add them together using superposition. All right. So remember, if you are convolving with an impulse, it is just like the identity function. Okay? I hope there's some other part. The signals is fun.
Signals is there. We're at our last. We only have one center.
2 weeks left to go.
All right. So where Dr. Vid left off, I just want to sort of recap a little bit. So last week, what you should have, or on Wednesday, what you should have talked about, where if I'm given a function x of t, that I define as cosine of 2 pi f t. If I want to sample that, this becomes x of n equals the cosine of omega n. Right? Stop me if I've skipped things that you haven't talked about yet. But I got like the 5-minute version of what you've done so far from Dr. Vid. I don't know exactly what that entails.
We just got into aliasing.
Okay.
At the end of the.
So we all know then that omega is defined as 2 pi f over the sampling frequency, right? So far, so good?
Yep.
All right. Yep.
Is n the sample number?
N is the sample number. Yeah. So if we want to convert between n and t, right? How do I do that?
N times delta t.
N times, okay, so n over the sampling frequency gives me, wait, is this right? Let me think here. The amount of time between samples is equal to, yeah, n times, right. So we were doing right. Okay. Divide t by fs. Yeah, I'll go right. All right, so when we picked off, when we were talking about aliasing then, if we draw out a cosine, if we're looking at if we're plotting x of n equal to cosine of capital omega n versus omega, what does this look like?
Bunch of sticks.
Not six. I'm just plotting x of capital omega times n. Sorry.
Oh,
This up.
versus
This is
omega.
clearly-
Just regular cosine?
It's just a regular cosine.
In the sample domain.
Of course, like the projector stuff is totally disappeared now. Whatever. Go away. Yeah. Yeah. I hate this stupid thing.
It's not one of those things you can pull it down.
No. No, I don't want to turn that off. Ooh, there we go. Keep screen up.
Dr. B had to set a Jurassic Park style.
Okay. So if I'm plotting this, it looks like a cosine.
Mm-hmm.
So where do I start?
At
So I start at 1, and what happens? Okay, so we know it looks something like, yeah, so what I want to look at here is pi. So what you should have talked about in class on Wednesday is that if you look at a point here, let's say this is 0.8 pi, and you look at a point here, which is 1.2 pi, okay, these should be equal, right? So x of n is equal to cosine of 0.8 pi. It's the same as cosine of 1.2 pi. Right, and that's true also if I include any value of n. Right, so that's just like another harmonic. Right, as long as I keep that constant for both of them, that's the same thing. Okay. So this leads us to what we call aliasing, right? Where you can have two different things have equivalent values, which is not good because there's no way to distinguish between them. Right? So what we want to talk about today is how do we sort of distinguish between those two. What do you mean notes? Okay. So let's actually look at this math problem. So I have some code here. Okay. So I won't worry too much about the code, but what I want to show you is what we're looking at. Okay. So all right. So let me just describe a few things here. So first of all, we're defining the frequency of our continuous signal, a frequency of 10 hertz. Right. So don't worry about too much about the syntax here. This is basically just defining a function. But we're going to sample this cosine with a sampling rate of 15 hertz. Okay. And we want to see what happens. Right. Okay. So our blue signal is our original cosine. Okay. And the yellow dots represent the number of samples. Okay. So let's see if we can make sense of this. So the first thing is that is this correct? Right? Like, is the period of this correct? 10 hertz?
No.
Okay. The 10 hertz of the newly created is not. Blue looks good. Okay. Remember that for the yellow points, we're sampling at 15 hertz, right? Which means that there are 15 per second. Okay. So we should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for 0.6 seconds. The red one is if we were to take the sampled points and reconstruct a cosine, that's what it would look like. Okay. So ignore the red for now. Just look at the points. Okay. Because we're sampling at 15 hertz, right? And this is technically undersampled. So what's happening is when you look at the yellow points, if you tried to fit a line to that or fit a curve to that, that's why you're getting the red signal, which looks totally shifted. It's because it's aliased. All right.
Looks stretched out.
Or stretched out, yeah. Okay. Right. It's actually a different cosine. Yeah, it's not just shifted. Yeah. Okay. So down below we have a plot of if we're looking at. Did Dr. Bay talk about how to sample? Or not so much.
In MATLAB?
No, I mean like the actual sampling process, like how you generate samples, like using the impulse train. Did you talk about that?
Nope.
No.
Okay. All right. So quick lesson on how we sample. All right. So if I want to sample, right? Let's say I have some continuous time signal that looks like this. Yeah. Okay, so this is my x of t. And this is my. Okay. So if I want to create a digital signal from this, like if I want to take samples from this, what I'm going to do is I'm going to multiply this whole piece by an impulse train. So if I multiply these two together, I'm not convolving, I'm multiplying. Okay. If I multiply those two together, what do I get?
Are those unit impulses?
Yeah, those are unit impulses.
And all equal.
Do they have to, the duration have to match the S of t then?
Well, I mean, assuming that, this end, let's just say it ends here.
Yeah.
Okay. Like, it doesn't matter. I mean, you're multiplying by an infinitely long impulse train.
You're only going to get the value of x of t at each impulse.
Right, so you're going to get something that looks like this, right? And then, this is probably a little bit higher. I'm drawing this really poorly, I apologize. But basically what you should get is impulses that have the same magnitude as whatever x of t is at that value. Okay? So you can label this in two different ways. You can label this as having an x-axis of t, or you could label it as having an x-axis of n. Okay? So if it's t, this is the same as 1 over, these are spaced at 1 over sampling frequency. Okay. So if my sampling frequency is 10 hertz, then these should be at every 0.1 second. Okay. So, or in this case, if fs, we have is 15 for our code here, so t should be 1 over 15, which is, I don't know, 1/3 times, it's like 0.06 or something like that. So, okay, that makes sense. So this is equal to roughly 0.6, 1.2, sorry, 0.06. And so on and so on. Okay? Or I can label this as samples, where this would be n equals 1, n equals 2, 3, 4, 5, 6, etc. All right. So to actually sample, all you're doing is multiplying everything by a series of impulses. So what our goal for today is to sort of look at aliasing both from a time perspective and also from a frequency perspective, if we have time. We'll see. Okay. So the plot on the lower axis then is what we get when we multiply our impulse train that has impulses every 0.06 seconds. Okay, when we multiply that by our input signal, these are the samples that we get out from that, okay, which correspond to the yellow points in the top graph. Okay, does that make sense?
Mm-hmm.
All right, do these look like they're spaced every 0.6 seconds? Okay, so then, yeah, so 0.06 seconds, sorry. So in 0.6 seconds, we should have 10 samples, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So that looks good to us. Okay. Okay. So when we actually, what I was saying before is if we actually fit a curve to these points, we then get an aliasing signal. So what we want to look at now
John, what if this were not a cosine, the blue signal? What if it were like a triangle? How would it be able to interpret the difference?
well, we want to look at a cosine now because it's only got one frequency in it.
Okay.
So if you're looking at
Triangle.
look at triangle waves or square waves, how many frequencies?
More than one.
Right. Infinite, right? So no matter what happens, something's always going to get aliased.
Wait, so basically for each frequency, it's going to be implicitly interpreted as a cosine?
You can think of it that way, right?
Okay.
It's a sum of cosines, right?
Yeah.
So if you sample a sum of cosines, certain cosines will be fine, and others will be aliased, right? Because technically you have cosine of, up to like infinite frequencies. So as long as you sample at a really high frequency, the vast majority of the important components won't get aliased. All right, so what I'm going to do here is I just want to show you what happens to the graph. I got this. Okay, so as I increase this,
Probably make that stay on top. Right.
Windows doesn't have that.
Doesn't have the.
Windows is stupid. But the point is, as I'm increasing my sampling frequency, you can see that I'm getting closer and closer to my original signal. Okay. Right now, I've hit almost just about 20 hertz, right, for my sampling frequency, which is right at the Nyquist frequency, right? That satisfies that the sampling frequency has to be double the frequency of the cosine. Okay. So now we have a pretty good fit, right? If we go up even higher, right, our fit's a little bit better. Okay. It's not changing, right? The red curve is now totally within the blue curve. This is what we like. Okay. So you can just keep going up, whatever you want. The more samples you have, the better the fit you get to the curve.
It's like one of those traffic diagrams.
Yeah.
Isn't there only one possible cosine that can be associated with the sampling? I mean, even at a lower sample frequency.
No, because what we were saying, if we change this back to 15,
Yeah, once you get to a certain point, you're not really gonna have a cosine. Once you get rid of the aliasing,
oh, right.
going
So,
further is kind of useless.
No, there's some
No.
benefits to oversampling.
No.
It depends on what you're doing. The more samples you have, the more accurate, the better the recreation that you get, right? It depends on the application. Sometimes you're like, okay, I don't care. Like, for all you care, you could have exactly, this is 20. This is the absolute most basic case, right? So what if I wasn't, like in this case, I fit a cosine to these points, but what if you're just trying to fit any generic function, right? Like maybe you don't know it's cosine, maybe it's just whatever. Okay. In that case, right, that's just like a triangle wave. It doesn't get you a very good depiction of your cosine.
Or if you were trying to fit a sine to this instead of a cosine, then you would just have impulses at 0. Wouldn't you?
No, you'd still have, yeah,
It's
it'd
the
just be,
same
it'd be a
function,
phase
but
shift.
It would be a phase shifted.
Yeah.
Do we always do this digitally? We can't.
Hmm?
We can't do this like analog.
Sampling is by definition digital, right? Because you're breaking a continuous signal into discrete points. So when you actually think about everything you do in MATLAB is actually digital. But we approximate it as being continuous by giving these functions like huge number of points, right? Where you'll define your time or your frequencies to be like, between 0 and 10, but you might have like 100,000 points in it, something like that, right? Where it's so highly sampled that you can approximate it as a continuous signal. All right, so that's sort of like our time demonstration. Now I want to talk a little bit about how we can look at it from the frequency perspective. Okay. So now imagine, actually let's just stop and recap. So aliasing basically means that if you are not aliasing, you've preserved all the unique characteristics of your original signal, right? If you do start to alias, then it's no longer preserved because you have one signal that is equivalent to another signal, right? That have different, very different frequencies. So our goal is to just maintain sort of that uniqueness. Right? So if we want to look at this from a frequency perspective, let's assume
Fail. Projector fail, not TI fail.
that's what I had done before. Watch, it'll be back.
Yeah.
Goodbye, projector.
This room is haunted.
Why won't you turn off? Now it's pissed. All right. So, let's just take any generic signal. Okay, like who cares what it really is? Why do all my markers? You know why all my markers suck? Because I have to do this stuff real big. Not that it's his fault, it's because they don't supply markers.
Then you got your bad.
Cedric has some.
Yeah.
I've got Cedric's got something.
Yeah.
Let me see if this green one works. Oh, that's great. I always have like 3 or 4 of them on hand for this very reason. you guys know like dry erase markers can actually erase dry erase markers?
Really?
Because they have solvent in them. That's why they dry erase. So when they start drying out is when they start leaving marks like that. And also when the board hasn't been cleaned in forever. Anyway, so I have some signal x of t. I don't really care what it is. Okay, and we said that the equivalent of sampling is by multiplying this by an impulse train. Okay, whatever. Okay, so ideally for something that's as like a weird and complicated signal as this, you need a pretty high sampling frequency to really be able to capture it, right? As it is, you get something that looks, not all that great. But the whole point is that I'm multiplying here. So now I want to look at it from a frequency perspective. So let's just assume I'm not even going to bother trying to figure out what that whole Fourier transform looks like. I'm just going to approximate it. So I'm going to say that it's band limited, which means that it has to lie between two different frequencies. And let's just say, for our intents and purposes, that it looks maybe like this. Right between negative B and positive B frequencies. Yeah. This is okay. So now I need to take the Fourier transform of an impulse train. Anyone know what that looks like?
A bunch of constants.
It's going to go to infinity.
I mean, it is going to go to infinity. Yes.
They're all going to add
Uh-huh.
together on top of each other.
Yeah, it's a constant, right?
It's a whole bunch
So
of
what's the difference
constants.
between taking the Fourier transform of an impulse train
Some of these steps.
versus taking the Fourier transform, Fourier, I'm sorry, yeah. Let me think about this. Would you use the Fourier transform or the Fourier series for this? Is that impulse train periodic? Does it repeat itself?
Mm-hmm.
Absolutely it does, right? And how often does it repeat itself? Right, this is 1 over the, or technically we can say it as n, right? Okay, so if I want to actually take the Fourier transform, or really it's the Fourier series in this case, how would I do that? Going back in time, let's
1 over the period.
1 over the period.
Mm-hmm.
Integral over the period.
So okay, so x of t in this case is just
Delta.
yeah, it's like delta t minus some constant where that constant is n over fs, right? So really, it's actually it's just
Well, you have some at 0. You have one at 0.
yeah, but you can have n equals 0.
Okay.
Okay, or I mean, we can define n equals 0. We don't really care. Okay, it's not all that important. Times e to the minus yeah.
So
Okay.
a squared.
So what do we remember? Okay, so think back to some of the convolution problems that we were talking about, like when you convolve anything with an impulse, right? You're basically doing this integral, and what do we say that integral amounts to?
It'll just be evaluated at the exponential at the area. No, where the pulse is shifted.
The delta function times e to the negative j omega n.
Close. Well, okay, so what we define, okay, this is just like a mathematical definition, where this integral is equal to whatever the coefficient is of your delta function. So in this case, the coefficient for our impulse train is just 1. Okay? What? That's what you said? Alright, so anyway, so this whole thing just goes to 1. Okay? So this is equal to
N equals 0, right?
what?
N equals 0.
For any any value. It's like the definition of when you integrate a delta function.
Mhm.
It reduces to whatever the coefficient was to the delta function.
Well, I think if, for instance, if n were something else besides from 0, it would be e to the negative j.
Right. I don't know the actual like proof behind it. I'm just saying that this is like a definition where the integral of an impulse times anything, okay, is just equivalent to the coefficient of the impulse originally, which in this case we said it is 1.
With
Okay. That's for anything. Okay. So what this comes down to is 1 over period. What's 1 over the period? The period is n over fs, right?
Mm-hmm.
So this is
Thanks.
right, is that right?
Mhm.
Yeah.
At first,
Okay.
it's one of the changing
Hmm?
period.
Fs is the sampling frequency.
That was so much one of the changing.
So, okay, so I'm sampling this at this with some frequency. Who cares what it is? Okay. It's just that it means that every, n over fs seconds, I get a new sample. Okay, so for the first sample, for example, when's that going to happen? If let's say fs is equal to 10. Okay. So n, t, okay, so n is 0, t is 0. When n is 1, what is t equal? 1 over 10, so 0.1. When n equals 2, what does this equal? 0.2. Okay, you get what I'm saying with this now? Guys, still a little lost. Okay. Make sure I'm following what he wants me to do here. Totally off. Okay. All right, so this is my answer. So another way to sort of interpret this is that my frequency is equal to n times
One over t is the frequency, isn't it? Or so isn't it just equal to f over s, or fs over n? That's 1 over the period, not 1 over function.
So the frequency is equal to the transform.
Okay, so actually another way I can interpret this is that the frequency of my samples, so this corresponds to the period of the samples, so the frequency of the samples is equal to n times the sampling frequency.
Is that fs over n the frequency though? Is it 1 over t?
The t is the period. That's
T is
what I was-
period.
It wasn't defined. That's what I was.
Didn't we define t equals nfs earlier?
Let me see here. We did kind of jump at a whole bunch of steps here. Okay, sorry. Okay, so that's the magnitude of my Fourier coefficient. So what I'm now trying to apply is where do I place those, right? Because that's just a constant, right? Where I'm like n changes, but ultimately it's a constant. So we know that the Fourier transform of this is going to look something like a bunch of impulses. So the question now, we know that this value is fs over n. Wait, no. This should just be, sorry, this should not be a function of n. giving you guys quarters. Don't worry about that. Sorry, this is, okay. This is the sampling period, right? So there actually shouldn't be an ending here. This should just be straight up FS. Okay. Because the sampling period doesn't change as a function of n, right? Because the sampling frequency is constant.
Okay.
Yeah. That was my mistake, sorry.
Well, if FS was over n, and let's say, n was like equal to 1, would that just mean like that's how many points?
Let me try to rephrase that, okay? So the sampling frequency corresponds to the spacing between these impulses, right? So what I'm saying is that as n increases, am I changing the spacing between them? No, it's staying constant, right? So that means that the sampling frequency or the sampling period, whichever one you want to interpret, they're basically the same thing, does not change as a function of n. Right? Like as you go farther out, the spacing stays the same. You see what I'm saying, Justin? So the whole point is that this sampling frequency, so this is n over fs, right? Or in this case, it's like, let's not use n. Let's just say 1 over fs, this is 2 over fs, et cetera, right? But that spacing between them is still 1 over fs, right? We don't know, we don't care what that is.
Mm-hmm.
So what I was saying here is that when I was doing the Fourier series of this should have been the sampling period.
Okay.
Not just like a generic period.
Mm-hmm.
And then 1 over the sampling period is equal to the sampling frequency. Okay. So this is one thing. So when I take the Fourier transform, okay, I now know that my impulses have a magnitude equal to my sampling frequency. Okay, and now I'm trying to figure out where are these points. Okay. So the way that you can interpret this is now this is n times fs.
It's the Fourier transform for the one on the left.
Yeah, so this is, we can imagine this is the band limited Fourier transform of this guy. We're just whatever. We don't care what it looks like. We're just trying to give it an easy example. And then this is the Fourier transform of this guy. So the Fourier transform of an impulse train is an impulse train. Okay. The magnitudes change and the spacings change, but it's still an impulse train. Okay.
So the magnitude is fs then?
Hmm?
So magnitude is fs and
Right.
the spaces is n times fs.
Right.
So that's why you're saying it gets spaced out further as it goes out.
No, it doesn't. I'm just saying that the the actual frequency here is determined by the sampling frequency and the number of the sample.
So when it gets bigger, let's say like at that point if n was 1 and then n was the next one be n was like 2 times sampling frequency.
No, because it's just for its location on the axis, right? So if n is 1, fs is 10, then this is going to be at 10. So the next sample, it's going to be 2 times 10, so it's at 20. The next one's at 30.
So it's just the inverse.
So the spacing's not changing.
Okay.
Okay.
Just the inverse
I'm
of
just-
the period of the original train.
Right. Yep.
I'm kind of curious. If we examine X and T, we just call them aligned to our Fourier transform rules. I would imagine that since we have a limitation on our sampling frequency, what our frequency thing is, why do we still have pulses? I thought they turned into one.
Because these are 2 independent things right now. We're not worried, right? This is the Fourier transform of that. This is the Fourier transform of that. That's all I'm saying. Okay? They're not related yet. Okay, so the last thing we're out of time, but the last thing I want to say here, to drive home the point, is that if I'm multiplying in the time domain to get my signal, what do I do in the frequency domain?
Convolve.
Convolve it. Okay? When I convolve this guy, what does that look like?
Bunch of
Right, it should be a bunch of triangles. So the point is that I should get something that looks like, and so on out to infinity, right?
Mhm.
So the whole trick is that if this spacing is big enough, there's no overlap between these pieces, right? So everything is still maintained, right? Like the unique properties of that signal are maintained. If this is much smaller, right, and now I have something that looks like so, right, superposition kicks in, so now I have to add those signals together, which means that I no longer have the original signals information.
I see. Okay.
Right.
Okay.
Right, because the labels on here are n times fs, right? So if fs is too small, then that means your spacing is very close, and then when you convolve them, there's overlap between those.
Mm-hmm.
I gotta say, that seems kind of contrary to what we previously learned when we had sticks in the time domain to be a constant.
That's because you weren't looking at a periodic signal. Okay. So before, when you did the Fourier transform is the same thing minus the 1 over t, right? And you only have like one impulse. You know what I'm saying? So that's why it goes through the constant.
Mm-hmm. Okay.
Anyway, this is all in the book. I'd highly recommend reading through it. It is lecture 34 and 35. So check it out. We're out of time. But I hope that was at least a good intro to it. And ask Dr. Bates questions if you still have them.
Cool.